In this lesson, we're going to learn about circular functions and the unit circle. So recall our initial definitions of our 6 trigonometric functions in standard position. So starting with sine of theta equals y over r. So if you'll remember, what this means is if we had an angle in standard position and that angle was theta, then there's a point where you could drop a right triangle to the x-axis. The y value is the opposite side to that angle. The x value is the adjacent side to that angle. And r is the distance to this particular point that we're looking at. So the radius. So if you use your definitions of sine, meaning sine of theta is the opposite side over the hypotenuse, you get y over r in this setup. So that's where we're coming from. Cosine of theta is x over r. Tangent of theta is y over x. And then of course we have our other functions. Cosecant is the inverse of sine, r over y. Secant is r over x. And cotangent is x over y. These functions are based on a circle centered at the origin of any radius r. But if we place this function on a unit circle, which is a circle whose radius is 1, then these definitions simplify to sine of theta equals y. Because if r is equal to 1, we get y over 1, which is just y. So that's a little bit easier to recall. Cosine theta equals x. Tangent theta doesn't change because it didn't depend on r, but it's y over x still. Cosecant is 1 over y. Secant is 1 over x. And cotangent is x over y. So it just makes our functions a little bit simpler to remember. And if we create a unit circle with all the common angle measures we have explored, and label the coordinates of each point, we create a very convenient method of evaluating our trigonometric functions at all of these common angle measures. So this is the unit circle. And this is a circle whose radius is 1. And I have labeled all the common angle measures, both in degrees and radians. And I've labeled the locations of each of those, the coordinates of those points. So we've gone through how the angle measures are derived. So I'm not going to repeat that. But let's talk about how the points are derived. So starting with some easy ones. The quadrantal points. Since we have a circle of radius 1, it should make sense that, starting from the center, and if we go 1 unit to the right, that'll land us at the coordinates 1, 0. So where x is 1, y is 0. That's why the coordinates of that point exist as they are. Same thing if we go up 1 unit. Then I haven't gone anywhere in the x direction, but I've gone 1 unit in the y. So 0, 1 for that point. And similarly for the remaining. That's why this point coordinates are -1, 0, and finally 0, -1. So that's where those points come from. Let me get rid of them so I can show you where the rest come from. Let's start with pi over 4. So this coordinate right here. So I can make a right triangle, and I'm making that right triangle with respect to the x-axis. That's always how we will do these things. So this is a 45-degree angle or a pi over 4 angle. That's equivalent, because remember, if you take 45 degrees, multiply that by pi over 180 degrees, 45 goes into 180, 4 times. So it's an equivalent angle measure of pi over 4 in radians. So because that angle measure is 45, and this is a right triangle, this other angle measure is also 45 degrees. So this is a 45, 45, 90 triangle. And I'm on the unit circle, which means this distance from the origin to this point is 1. And because that distance is 1, and I know the ratio of sides for a 45, 45, 90 triangle, so for 45, 45, 90, it was, the ratio of sides was 1, 1, square root of 2. And the square root of 2 was opposite the hypotenuse. Well, the only problem is the distance on the hypotenuse is 1 and not the square root of 2. But that's easily corrected just by dividing each of these through by the square root of 2. Okay, so that makes this distance 1. The middle distance, 1 over the square root of 2, if you rationalize that denominator, so if you take 1 over the square root of 2 times the square root of 2 over itself, you get the square root of 2 over 2. So this is the square root of 2 over 2, and this is also the square root of 2 over 2. And I can do that to this ratio of sides because as long as I multiply or divide each one by the same angle or the same distance, it won't change the ratio of sides. It'll just change their form. So that means the side opposite my 45 degree angle measure is the square root of 2 over 2, and the side adjacent to it is the square root of 2 over 2. So this is a y value, and this is an x value. So if you'll notice in my coordinates, I have the coordinates x is the square root of 2 over 2, and y is the square root of 2 over 2. That's where that particular coordinate pair comes from, that point. Okay, let's look at another value. So let's look at 30 degrees, pi over 6. So again, I have the distance from the origin to that particular point is 1. If I drop a reference triangle, right triangle, to the x-axis, then I'm in the setup to where this angle measure here is 30 degrees, or pi over 6. So that means this angle measure is 60. So I'm working with a 30, 60, 90 triangle. So on a 30, 60, 90 triangle, we know the ratio of the sides to be 1, square root of 3, 2. Now, the side opposite my 90 degree angle is 1. It's not 2. So to make it 1, I'm just going to divide all of these by 2. So that tells me 1/2 square root of 3 over 2 and 1. So the side that's opposite my 30 degree angle is 1/2. The side that's opposite my 60 degree angle, or adjacent to the 30 degree angle, whichever way you want to look at it, is square root of 3 over 2, and then of course the hypotenuse is 1. Since this is a y value and this is an x value, that tells me why the coordinates of this point is square root of 3 over 2, 1/2. You can make a very similar argument for the 60 degree angle measure. All you would have to do is just reverse things. So the radius is 1. The angle measure here is 60. So the angle, or the side length that's opposite 60, as we discovered, is square root of 3 over 2. Since this angle measure is 30, the side length opposite it is 1/2. So the coordinates x is 1/2 and y is the square root of 3 over 2. So that's where all of these values are coming from. And you can do this all the way around the unit circle, but we're just simply not going to. It'll take too much time. Now, from here, what I want you to notice is symmetries. Now, first thing is, if you look at the coordinates square root of 3 over 2 and 1/2, square root of 2 over 2, square root of 2 over 2, and then the 1/2 root 3 over 2. There's a mirror image of that point over here in quadrant 2. Okay? So all of these are mirror images. Only difference is negatives and positives. But here are some things that we know about that. First, we know in quadrant 1, x is greater than 0 and y is greater than 0. So that's why you're seeing all positive values here. In quadrant 2, x is less than 0 and y is greater than 0. So if you just knew that particular fact and the symmetry here, you can derive all these points from the ones in quadrant 1, and all you have to do is just put negatives on each of your x values. That's the only difference here. Next up, if you look down to quadrant 4, this point going downward, this point going downward, this point going downward. There's symmetry here as well. And it's the same kind of symmetry. But the only thing you need to know in order to figure out whether your values are supposed to be positive or negative, let's just keep going around. For quadrant 3, x is less than 0 and y is less than 0. And in quadrant 4, x is greater than 0 and y is less than 0. So it's the y values that are negative in quadrant 4. So as long as you know that, along with the symmetry that's occurring, it's very easy to come up with the values of these points. And then similarly, you can get quadrant 3. You know, there's symmetry both directions here. So if you go this direction, it's symmetric. And if you go from quadrant 4 back, it's symmetric. There's a whole lot of symmetry that's going on in the unit circle. And so once you come up with the values in quadrant 1, you can derive the values in quadrant 2, 3, or 4 from those. Now, another way of thinking about things, if you don't want to go with symmetry, which is fine, different approaches work for different people, you can always use reference triangles. So for instance, if we're looking at this particular point, 120 degrees, if we draw a reference triangle, so this is 120 degrees this way, this reference angle right here is going to be 180 minus 120, which is 60 degrees. So then in a 30, 60, 90 triangle, opposite the 60 degree angle is root 3 over 2. Opposite the 30 degree angle is 1/2. The only thing you have to kind of consider is, since you're in quadrant 2, your x value is going to be negative. And then that derives the coordinates of this particular point. X is negative 1/2, y is root 3 over 2. There's all kinds of ways of coming up with these. Now, one last thing I want to show you is on the calculator. If you key in, for instance, let's say sine of, oh, and let me check and make sure I'm in the correct mode. All right, I'm in degree mode, so I'm going to use degrees. So sine of 30 degrees. I get 0.5, which should make sense because here's a 30-degree angle measure. Sine is the y coordinate, so 1/2 or 0.5. Similarly, if you're in radians, that's perfectly fine. You have to be careful and make sure which one you're in, because if you do sine of pi divided by 6, that's equivalent to 30 degrees. You'll get the exact same answer. But if you're in radian mode and you type in degrees, you get something wildly different. So you have to really be careful and just make sure you're in the correct mode setting. I'm going to continue in radians for this remaining example. Okay, let's try the cosine of pi over 6. I get a seemingly random answer, 0.8660254, and it kind of goes on. But I know it's supposed to be square root of 3 over 2, so let's look at that. So if I do the square root of 3 divided by 2, notice it's the exact same answer. So the square root of 3 over 2 is approximately 0.8660. Similarly, if I do sine or cosine of pi over 4, which is an equivalent 45-degree angle, pi over 4 that is, I get 0.7071. So that's approximately what the square root of 2 divided by 2 would be. So you're coming up with the decimal approximations to these values using the calculator. What is nice though is going this direction, it'll adjust for the quadrant as well. So for instance, if I put in, let's say, cosine of 5 pi over 6. So that's in quadrant 2. The x values are negative in quadrant 2. So it knows that the value should be negative square root of 3 over 2. So the calculator can be helpful. You just have to understand that it's giving you approximations rather than exact values. And sometimes in your homework, you'll be requested one or the other. So in a lot of applications problems, approximations are generally fine as answers. But in other problems where it says to use exact answers, you need to answer with square roots and pi, that sort of thing, for your final answer. Now, since we know how the unit circle is set up, let's take a look at how it can be used to come up with values. So for instance, let's use the unit circle to evaluate the sine of 3 pi over 4. So let's say I'm taking a test and you won't have a unit circle provided for you for the test. But I highly recommend the first thing that the first thing you do is to draw out a unit circle and at least sketch what's happening in quadrant 1. And then you can answer these types of questions very easily for the rest of the quadrants. So the sine of 3 pi over 4. So 3 pi over 4 is right here in quadrant 2. The sine is the y coordinate, which means the answer here is the positive square root of 2 over 2. I'm just answering with the y coordinate of that particular point. Part B, the cosine of 5 pi over 3. So I'm just going to find 5 pi over 3 on my unit circle, and the cosine is the x coordinate. So the x coordinate of that point is 1/2. Tangent of negative pi over 6. So I don't have any way of coming up with a solution for negative pi over 6 because I don't have negative pi over 6 listed here. One thing I could do is I could try and come up with something that's coterminal. So coterminal to negative pi over 6. Remember, in degrees, what we would do is just add 360 degrees, which is one full rotation. In radians, we can add 2 pi, which is one full rotation, to find a coterminal angle. So I need to get a common denominator. So it's negative pi over 6 plus something over 6. So it looks like it would be 12 pi over 6. And that would be 11 pi over 6. So that means I'm working with this angle measure right here. That's its equivalent. So that means the solution here is, remember, tangent is y over x. So the y coordinate is negative 1/2. The x coordinate is negative square root of 3 over 2. And I just need to simplify this fraction. So instead of dividing fractions, we invert the denominator and multiply. Fix that 2 so you can read it. So this would be times 2 over the square root of 3. The 2's cancel out, and I would end up with negative 1 over square root of 3, but I need to rationalize my denominator, so I'm going to go ahead and multiply in square root of 3 over itself. So negative square root of 3 over 3. So when it comes to the other trig functions, it's not quite as convenient to use a unit circle as it is for sine and cosine, but it's still a whole lot easier than setting up a triangle and trying to go that way. Another way you could have approached this is if you knew that this was a negative rotation of pi over 6 or negative 30 degrees, then you could just use that point without having to come up with a coterminal angle, because technically you've drawn an angle of that measure 11 pi over 6, and that's what is coterminal with it. Either way is fine. Here are a few more examples, starting with the secant of pi. So pi is my straight angle, the equivalent to 180 degrees. Secant I have to think of as secant is 1 over the cosine. Cosine is the x-coordinate. So secant is 1 over the x-coordinate. The x-coordinate here is negative 1. So in this case, it's going to be 1 over negative 1, which is negative 1. Cotangent of 3 pi over 2. So 3 pi over 2, I find it right here. Again, it's a quadrantal angle, just like the pi angle measure. And in this particular case, the cotangent is x over y. X in this case is 0, and y in this case is negative 1. So 0 over negative 1, cotangent of 3 pi over 2 is 0. F, cosecant of 0. So 0 is just a 0 degree angle measure, so I'm right here. Cosecant is defined as 1 over y because it's the inverse of sine, and sine is the y coordinate. So the y coordinate here is 0, which means I have 1 over 0 or undefined. And as you'll recall, there were many locations along the quadrantal angles where our functions secant, cosecant, tangent, and cotangent resulted in being undefined. So that's reflected here as well. Here's another type of an example which goes in the opposite direction, it asks us to find the exact value of s in the interval pi to 3 pi over 2 inclusive that satisfies tangent of s equals the square root of 3 over 3. So, in order to figure this out, first I want to just kind of notice that s is given as my variable to solve for, and the reason is s is the arc length, and so we're looking for an arc length instead of a angle measure. So sometimes they use s, sometimes they just call this x. It doesn't really make a whole lot of difference. Now, the angle measures pi to 3 pi over 2. What that means is we're restricting ourselves to quadrant 3. Okay? So, any solutions that may occur outside of this range, we are going to ignore. Now we want the tangent of this arc length. Oops. So the tangent of s, we want it to be the square root of 3 over 3. So if we look at the different values that we have, square root of 3 over 3 isn't any of them. Okay, but the coordinate pairs that are given, the x and y coordinate pairs, only would give us values of sine and cosine separately, not tangent. We would have to figure out what the value of tangent is for each one. Now, we do know that tangent is, tangent of theta is y over x. So there's a couple of there's one possibility I could rule out here. Now, I could definitely rule out the angle measure pi, because there y over x would be 0 over 1, which is 0. So that's not my angle measure. I can also rule this one out as well, because y over x here would be negative 1 over 0, which is undefined. So, not that. All right. In the 5 pi over 4, if the x and y values are the same, the tangent of that angle measure is equal to 1, because when you divide those two together, you know, anything divided by itself is just 1. So it's not that one either. So it's going to be either 7 pi over 6 or 4 pi over 3. Let's figure out which one it's going to be. So basically, we could either set up a right triangle at this point and then determine, you know, which angle measure works, or if we didn't want to use a right triangle, we could just start dividing the coordinate pairs. So like at the tangent of 7 pi over 6, for instance, that would be the y value, which is negative 1/2, over the x value, which is negative square root of 3 over 2. Start working this through. So negative 1/2 times negative 2 over the square root of 3. The 2's cancel. Negative times negative is positive. When I rationalize, which means if I multiply the result by square root of 3 over itself, I do in fact get square root of 3 over 3. So that means s is 7 pi over 6. And if I had used 4 pi over 3, I would have ended up with just square root of 3 as my answer, and I would have known that that wouldn't have been the correct value. So I'm just kind of using the unit circle to find out what I need. It's certainly much more convenient for sine and cosine, but you know, it can be done for tangent and the rest of the trig functions as well. In the last slide, I'd like to help you in coming up with ways of filling out a unit circle. Because when you approach a test, it's definitely going to be advantageous to you to go ahead and draw one out, fill out all the points that are necessary. It's going to make solving things a whole lot easier. Especially when we get into equation solving later on, a unit circle is really imperative to getting that sort of thing done in a reasonable amount of time. So first things first, I put my angle measures on here. So I just start with the quadrantal angles. So 0 degrees, 90 degrees, 180 degrees, and 270 degrees. And then I go in and start filling in my 45 degree angle measures. So this one's 45. 45 plus 90 is 135. If you add 90 more, that gives you 225. Plus 90 more would give you 315. And then I go in and start filling in the 30 and 61s. So this is 30 degree angle measure, 60 degree angle measure. You can't just add 90 every single time here, that just because like the distance from this angle measure to this one is not 90 degrees. It's actually 60 degrees, so you just kind of have to work your way through. One thing that you can do is if you go 15 degrees both directions from your 45 degree angle measure, that may help you. So like 135 minus 15 degrees is 120 degrees, plus 15 is going to be 150 degrees. So that's one way you can do this. Then 225, if you subtract 15, that would be 210. If you add 15, it would be 240. Then 315, if you add 15 degrees, that would be 330. If you subtract, it's 300. So that gives you all the imperative degree measures. Now, if you want them in radians, the one thing that I mentioned that you could do is basically, think of all of these as 15 degree angle differences. So in that respect, if you have, say, like 0 pi over 12, 1 pi over 12, 2 pi over 12, you just write these in at every single point. I don't know what that was. 5 pi over 12, 6 pi over 12. So if you do that for every single angle measure, then 0 pi over 12 would be the same thing as 0 radians. We don't need the 1 pi over 12. That's 15 degrees. That's not what we need. 2 pi over 12 would be pi over 6. 3 pi over 12 would be pi over 4. 4 pi over 12 would be pi over 3. And then 6 pi over 12 is pi over 2. And if you do this all the way around, you can get the different angle measures that are required for radians. I'm just going to go ahead and fill them out very quickly. So once you go through and you get all of your angle measures in degrees and in radians, then it's time to go through and fill out the coordinate pairs. So the coordinate pairs, I always start with the quadrantal angles because those are the easiest. And this would be 0, 1. This point would be -1, 0. And this point down here would be 0, -1. Then I fill out quadrant 1. Okay, so I know this point here is square root of 2 over 2 and square root of 2 over 2. This point here is square root of 3 over 2 and 1/2. Then this point here is 1/2 square root of 3 over 2. And I fill those out and I make sure those are correct. Even if I have to draw a right triangle or use, the ratio of sides of a 30, 60, 90 triangle to make sure I've got those correct, I make sure those are correct. Because everything else is going to be based off of those. So at this point, I don't draw in every single coordinate pair. At this point, what I do is just use symmetry, because you're never going to have a test that you need all of these angle measures. It's just, if you end up taking the test and you have 3 pi over 4 as a point, well, then I would come over here and draw in, based off of symmetry, what this would be. And just remember, in quadrant 2, the x coordinate is negative, but the y coordinate is positive. So it would be negative square root of 2 over 2 and square root of 2 over 2. So I just fill in those coordinates on demand. Just whenever I need them, I just use symmetry to develop what they're supposed to be. And that is how to make sure you have a good unit circle in order to answer your questions on any test. And let me remind you again, you won't have a filled in unit circle given to you for the test, but I highly recommend you start the test drawing a circle and filling it in right at the very beginning.